All right, let's go through this lab. This lab partner video is actually going to be a lot less than the first set because you've done all of these things before. So there's going to be a lot more pausing and you working than listening to me talk this time. So, all right. But I am going to point out a few of the twists that have to do with this lab for sure. So let's get started. The first thing you want to do is have your lab records ready to go. I'm not going to have mine out because I'm going to cheat a little bit, but also for sure have your lab instructions ready to go. That's what I have here, and your Pivot Interactive ready to go, and then also your lab records. Okay, the first thing that you are going to do is once you've got everything open, actually pause here, open everything up. Okay, is to talk about the brainstorm. So that's the first step. So I have my Pivot Interactive here. I'm just going to load something. And so it's asking you, what are 3 things you think could affect the period of this oscillating spring mass system is the formal word of what this is called. So, well, this is kind of lame because we're doing an interactive. So normally in the lab, right, you could test all sorts of things. We have tested a ton of things. So really this spring up here is our thing that we are testing. And there's so many different aspects of springs that you could test. But since this is an interactive, we're limited to what they're testing. And guess what the things are? This here is the spring itself. And it's actually going to be the spring constant of the spring. That's what this stands for. And we have the mass, that's how much mass they're going to hang from the spring. And then the amplitude is how far they're going to pull the spring before they let go. So those, I know it's really lame, but that pretty much does it for your brainstorm. So go ahead and pause right now and fill out that brainstorm. Okay, the next step is to fill out your design templates for each thing that you are studying. Remember, the dependent variable is going to be the period in seconds for all 3 templates. So go ahead and put period in seconds for dependent variable now. All right, and then the independent variable, you're going to have one for each thing you are studying in this lab. And go ahead and fill that out now. All right, for controls, the controls are going to be the other things that you are not currently testing. So let's say you're testing the spring constant. You then need to control for mass and amplitude. And so what you would do here is put, for your control, you would write mass, and then write which mass you are using. Please note, if you're doing spring constant and you choose to test A, B, C, D, E, F, okay? And by the way, I recommend B through G also, or some combination. Don't leave off spring G. Spring G is exciting. But you'll want to take a look really quick at, first click on amplitude number 1, but look really quickly at which masses you're allowed to use for each spring. Okay, because you want to find a control mass that is not grayed out, okay, for all of your springs. Otherwise you'll get in trouble. Like you want, let's say you pick 10 grams, right, as your mass. Well, the only spring that lets you use 10 grams is spring E. So that's a really poor control value. So maybe you pick 200 grams and that looks good. Like everybody can do 200 grams. So those are all sorts of, that's a tip for you for control variables. For amplitude, hi Mog, you for sure want to put the actual value of the amplitude that you use for your control. So you're going to have to go in and measure it with the little ruler like I showed you in the intro video. Okay. All right. Just a reminder, testable hypothesis is going to be a statement like spring constant affects period. That's it. We're not telling how it affects period. We're just saying it does. And then also the prediction then tells you how. Like, I think that larger spring constants will make the period shorter. Okay, so that's what you're going to do there. Okay. Let's pause now and let you fill out all of your experimental design templates. Okay, you got them? Awesome. The next thing are these questions that I ask in every lab that's formatted this way. What are the correct units to use for each of your independent variables? So if you'll notice, they might not match the units that are given in the Pivot Interactive. Okay, please stick to the correct physics units. Those include meters, seconds, and kilograms. Okay. One of the IVs is going to have units of newtons per meter, just letting you know that is cool. All right. Finally, number 4, are there any IVs that you'd like to study, like if you are actually in the lab? Are there things about springs that you would like to check out besides these 3 things? Or is there something crazy that you'd always wanted to try? Please think of one, and if you're having trouble brainstorming, totally reach out to a friend in the class and see if you both together can think of one. But list that one and tell me what effect you think it would have on the period of the spring. Okay, I'll give you an example in case you're really worried about this. Hi, Kat again. The example I have is what the spring's material's made out of. If I had a plastic versus, let's say, aluminum versus brass or a steel spring, would that affect what's going on? Just directly to try different materials. That's something I would like to do. Now, you can't use mine. You can't try different materials, but think of something else about springs that you would like to try and go ahead and list it there. And then finally, 5 and 6, the answers I have written for you right here. So just FYI, that's the answer, no tricks. But I do like you to know that answer and write it again and again just to rub it in. So take the time right now, pause the video and answer these design questions. All right, you are ready to actually take data for your lab. I have a few things to point out. First, here's the spring constants for each spring that is in the interactive. Notice they are not in order from lowest to highest. Okay, let's see. So what you're doing next is you're going to design your data table. Remember, okay, I want you to repeat each trial this time twice. I'm not making you do it 3 times because it is kind of a mechanical thing and it's unlikely that you'll get super different results every time because it's more computer-based. So you only have to do everything twice, but you do need to try 6 different springs, 6 different masses, and I know there's only 5 amplitudes, so 5 amplitudes. If there were 6, we would do them. Okay, so what you're going to do next is design your data tables. If you're worried about your data table, go ahead and check out your pendulum data table. This is going to be very, very similar, except it's just going to have 2 different measurements for each set. Okay, and then put your data into Excel and add those data tables to your lab records. So this is going to be the long pause. So go ahead, get all that data, put it in your lab records. I'll see you on the other side. All right, you got it? Nice. Now we're going to draw conclusions based on data only. I know this is very hard. You really, really want to look at a graph because graphs are amazing and we are mainly visual creatures as humans. Seeing the plots on a graph is a lot easier than just looking at numbers. However, the skill of being able to look at a set of numbers and draw conclusions is important, and that's what we're doing here. So just based purely on your data numbers, you're going to answer if your IV was positively, negatively, or not correlated. Remember, use those vocabulary. Please do not use words like directly or indirectly related to. That's not where we're headed right here. How does your data support your answer? Use numbers. You lost points if you don't use numbers, okay? So definitely use numbers and tell me your confidence level, and you're going to do that for all 3 variables, data only. Go ahead and pause and answer those now. All right, then now we're going to make the graphs because you are a visual creature and you want the graph. Go ahead and make the graph, but we are not adding a trend line. Dots only. We're stepping through this. I want you to be able to look at dots and not always see a line. I'm a little bit like frustrated because starting And this is no one's fault. This is how physics has been taught for the last 100 years. But everything is a line, and I hate it. I just hate it. I hate the term linearization, and I just have feelings about this. I think if you look in your physics textbook, I don't know, I should do some sort of statistical analysis. Look at your equations that you use the most often. How many are linear and how many are not? Why in the world do we expect everything to be linear then in the lab? Why has every single lab you've ever done since you were a baby been linear? Okay, I gotta get off. I'm getting a little dramatic. The cat's looking at me like, yeah, you're getting dramatic. Okay, but seriously, what I want you to build is a skill where you look at dots and you can see if it's maybe a curve and what kind of curve it might be. All right. So in this lab, actually, you're not going to get a line. Okay. Anyhow, what you're going to do then is do your graphs in Excel and insert them in your lab records, and then you're going to draw conclusions and confidence levels with graphs. If you can't remember how to do that, go ahead. What you're going to want to do is pull up the Pendulum 1 instructions and just take a look at those. But basically you're telling me like to do the dots go up and to the right together. Talk about maybe between dots, do you see sort of a positive slope or a negative slope happening, and is that consistent between pairs of dots? Those are all great things to talk about. So at this time, make your graphs, do your conclusions and your confidence levels. Don't forget confidence levels need percentages, and pause me and finish that part now. All right, you got your graphs, error bars. We are going to, once again, list what measuring instruments you use. This one in Pivot Interactives is pretty easy because you're just using 2 measuring instruments and they are on the screen here in your toolbox. So you're going to list those. But here's what's the smallest measurement each of these can measure. I kind of love this because one of these is an analog instrument and one of these is a digital instrument. So let's start digital. This instrument goes to the 10th, 100th, thousandths, 10,000th place. Okay, so the smallest measurement that this timer measures is 0.0001 seconds. Okay, so digital instruments, very nice, easy to figure out the answer to. Analog instruments, let me get rid of this little gray. This guy here, and this might be hard to see because it's small on the screen, but if I look at it, the smallest marking is 1/2 centimeter. It's not a millimeter, it's 1/2 centimeter is the smallest marking on here. So that's the smallest marking here, 1/2 centimeter. Okay, and those are the two things. Actually, I want you to include the mass here. And if you notice, the masses are all multiples of 10, like 10 grams is kind of the smallest mass. And so go ahead and just say 10 grams for here. Notice that it does not have a period next. It doesn't say like 10.0, it just says 10. So we're going to go with 10 grams as the smallest mass. Okay, so at this time, let's see, if you want to be totally like cover all the bases, I don't know if many of you will think of this, but also spring constants should be part of that, and these go to the 0.01 newtons per meter. So at this time, go ahead and answer those 3 questions now. Okay, next comes measuring technique. Now I really want to see how precise you are when you're using pivot. This is not a judging situation, okay? So like, let's say I have this pendulum here. Okay, I want to measure the amount of time it takes 5 periods and then divide that by 5 to get the time for 1 period, right? So how do I do this 10 times in a row? Well, what I want to do then is between each time, so let's say I already measured it, then I'm going to rewind all the way to the beginning. Okay, I'm going to take my stopwatch and reset it to 0. And then I'm going to go and figure out when she lets go. I'm clicking and dragging here because that's actually a little quicker. Okay, when she lets go again, so I'm going to figure that out again. And then set my stopwatch and then do the 5 periods again. Oh, my mouse isn't as fast as my arrow key. Okay. So I do my 5 periods again. 1, okay, 2, 3, 4, 5. And then find that time and write it down and do that 10 times, resetting this every time. Very, very critical to reset that every time because you might start it at a different time. So you want this to measure not only your like length of it, just I'm getting tangled up, but that's how you want to do this, okay? So you do that 10 times. It's going to take you about 10 minutes to do that, to get that data, okay? Then you're going to put it into Excel, find the standard deviation, put it in your lab records. Please go ahead and do that now. All right, the last bit here is to add the error bars. Okay, we're going to use that standard deviation as the error bars again in this lab. We are keeping it simple for right now because again, this is the first time you've actually quantified your errors in physics and I don't want to move too quickly. So we're still keeping it as the standard deviation here. So you want to draw your conclusions using your error bars. So look at the overlap and your confidence. And then actually after you're done with that, you have your overall conclusion. So that's it for simple harmonic motion 1. In simple harmonic motion 2, we're going to go ahead and get our math models again, check and see how well we did with those, but also kind of look at some fringe cases of the spring and how it's behaving. So can't wait. Great work.